Hello, everybody. Welcome back. Today we're going to be starting a new unit, Unit 9, which is the last unit in the AP Chemistry curriculum. So I hope you're ready for it. Let's get started. Okay, so for our final unit in this AP Chemistry course, here's our little factoid, which I think is just interesting that when astronauts come back from space, because there is less gravity in space, their spines actually expand. They are a little bit taller when they come back. Of course, that doesn't last, but I just think that's interesting. So, Unit 9, guys, is about thermodynamics and electrochemistry. Thermodynamics just means the exchange of different types of energy. We're going to pull multiple concepts back from Unit 6, which was on thermochemistry. And then at the end of Unit 9, there's a whole section on electrochemistry, which I imagine will be new to just about everybody in this course, new material. So what we're going to be looking at a great deal in Unit 9 is looking at different chemical reactions or physical processes and deciding, making a decision or a prediction on whether that process is spontaneous or not. And thermodynamics, the exchange of different types of energy, is going to let us predict whether that process is going to occur. It does not give us any information about how long it's going to take, but that's what we studied in the kinetics unit. We're not doing that here. But as I said, one of the things you're going to be asked to predict is whether a process is spontaneous. And the AP exam doesn't usually like that word spontaneous so much. They prefer the term thermodynamically favored, meaning a process that occurs on its own. It occurs without any outside intervention, without any help. You put the two reactants together and stand back, and voila, they produce products. Just as an example of, a thermodynamically favored process, if you place a ball at the top of a hill, a ball will spontaneously roll down the hill without any intervention. However, if you have the ball at rest, a ball at rest is not going to spontaneously move up a hill. In order to do that, you have to apply work, you have to expend energy. So we're going to be making a lot of predictions in this unit. And one of the concepts that we're going to use to help us make that prediction is a concept called entropy, which I imagine is probably a new term to most of you. So let's define it. Entropy, which has a variable of a capital S, is a measure of randomness or disorder. And you'll see that I've put this term in bold, degrees of freedom. That's the term that the AP graders like the most from what I have heard. So I'm going to try to use that term as much as I can. But let me just give you an example. Let's just talk about simple states of matter, solid versus liquid versus gas. And I want you to picture in your mind, think back to Unit 3 when we talked about the different states of matter. What do the particles look like? What is their behavior in the solid state versus the liquid state versus the gaseous state? And the entropy of a solid is relatively low. Solid particles are very often locked into a rigid structure. They have very little degrees of freedom, very little ability to move around freely. Liquids have a little bit more. And of course, gaseous particles are moving all over the place like crazy. Gases have the highest entropy because they have the greatest degrees of freedom. Okay, so in general, when we're talking about entropy of the different states of matter, gases will always be greater than liquids, which will be greater than solids. And one of the driving forces of a thermodynamically favored process is an increase in entropy. Typically speaking, if we're looking at a process and the entropy is increasing, meaning becoming more chaotic, more disordered, in general, things are increasing in their degrees of freedom, that usually will lead to a thermodynamically favored process. And we'll talk more about that in the next subunit. But one of the things that you will be asked to do, both in multiple choice and free response, is to make predictions about the changes in entropy for a particular process. So some of the things on the screen here are simple phase changes, some are chemical reactions. And just to be clear, what you're being asked to do is say whether the change in entropy, that's what I mean by delta S, is going to be positive or negative. For each process on the screen, we're going to talk through this. I want you to ask yourself, is this process becoming more disordered or more organized? If it's becoming more disordered, the degrees of freedom must be increasing. We're going to say that delta S is a positive value, whereas if the process is becoming more organized, degrees of freedom are decreasing, delta S will be negative. So let's look at each one individually. First one says a cube of sugar dissolves in hot tea. So think about the particles of the sugar. They're going from a solid form to a dispersed aqueous form. Degrees of freedom are definitely increasing. So the delta S sign would be positive. Again, guys, if this was a free response situation and you are asked to justify your answer, you want to use that term, degrees of freedom, and in this case, are increasing. Next one says a lake freezes over in winter. Okay, liquid to solid. Okay, crystallization is taking place. Degrees of freedom are decreasing. So that's going to give us a negative value for delta S. Rainwater on the pavement evaporates. Again, this is another phase change. We're going from the liquid phase to the gaseous phase. Degrees of freedom are increasing. That's going to be a positive value. Now these next three might look a little bit more complex. So let's talk about how do you make a prediction if we're looking at an actual chemical reaction. First thing that comes to my attention is the states of matter. Okay, we've got solid lead plus gaseous oxygen, and then on the product side, we've just got the one product, and it is in solid form. I can see that we've got some different states of matter here. Solid and gas going to one solid. To me, that looks like there's a decrease in the degrees of freedom. On the reactant side, we had some gas. On the product side, we have no gas. This looks like a decrease in entropy to me. Now this next one, everything is in the same state of matter. We have all gases. And if that is the case, ladies and gentlemen, what I want you to focus your attention on are the coefficients. Okay, on the reactant side, we have 3 total moles of gas producing just 1 mole of gas. So everything is gaseous, but we have fewer moles of gas on the product side. That tells me that there's going to be a decrease in the degrees of freedom. There's simply less gas. So I'm going to predict this would be a negative delta S. Last one, we have a solid dissolving into its aqueous ions. This is an ionic solid. Solid dissolving into its aqueous ions, and it tells me that that is an increase in the degrees of freedom. So I'm going to predict that that's a positive delta S. So that is a skill that you could absolutely be asked to do both in multiple choice or free response. If it's free response, you want to justify your answer using that phrase, degrees of freedom. So let's look at a practice problem for you to try on your own. I'll set it up for you. We have a heating curve given to us, and it says at 1 atmosphere, a sample of ice is heated to liquid water and then to water vapor. The heating curve is shown in the graph above. Predict the signs for the changes in enthalpy. Now wait a minute, let's stop there for a second. Let's review that word. That's calling back to Unit 6. Guys, remember enthalpy means change in heat. That was delta H. What they're really asking for is whatever process they're going to be showing us, is it endothermic or exothermic? Remember those terms? So they want to know, is delta H positive or negative? They also want to know if the entropy, delta S, for the process corresponding to segment X. Okay, so right up here, is the sign for delta S positive or negative? Going from left to right, and this is a free response, so you do need to justify your answer. Pause the video, see how you do with it. Okay, so first thing to make sure we know is what is even going on in this segment X. And if you go back and review things from Unit 6, heating curves, what's happening in that segment X is a phase change from liquid to gas, the vaporization process or boiling. Okay, so we're answering questions about the boiling process. So let's see, what did I say? So the enthalpy, the delta H, will be positive because vaporization is an endothermic process, a process that requires heat energy. Okay, so that's a review back from Unit 6. How about the change in entropy? I said it's going to be positive because the phase change from liquid to gas is an increase in the degrees of freedom. Remember, that's the term you want to use. Okay, so that would be a great sample free response kind of question. And then just one final thing, and we're going to talk more about this in coming subunits. But in general, guys, when there is an increase in entropy, meaning for whatever process you're looking at, if the delta S is positive, that is usually, please notice I say the word usually, not always, but usually, probably, a thermodynamically favored process. If the delta S is negative, usually, probably, that process is not going to be thermodynamically favored and in fact would be favored in the opposite direction. We're going to come back to this concept, as I said, in coming subunits, but I just want to make sure that that concept is clear. In general, in nature, in the universe, processes tend to become more chaotic. If you think about if you were to not clean your room for a month, and I mean like really not clean your room, like never pick anything up off the floor, don't make your bed, don't put your clothes away, leave trash on the floor. If you expended 0 energy over the course of 30 days, your room would become a very disordered, chaotic place. Things in nature tend to favor or tend to increase in chaos, in disorder. That's just how the universe tends to work. But again, we'll talk more about that in coming subunits. So that concludes subunit 9.1. I hope you guys have learned a little something about the concept of entropy, and I look forward to seeing you next time.